Good morning and welcome everybody to R&D Unplugged number 19. It's already our 19th seminar of the series. Today we have the pleasure of hosting Jean Vassoyan. Jean is a graduate of Telecom Paris and the Math, Vision and Learning Master's Program. He's currently pursuing an industrial PhD at Centre Borelli at University Paris-Saclay in partnership with the company OnePoint. His early research focuses on reinforcement learning applied to intelligent tutoring systems. More recently, he has shifted his attention to large language model, post-training, specifically exploring reinforcement learning with verifiable rewards and methods to optimize training tasks. Jean, over to you.
Okay, thank you very much, Howard. So, hi everyone. Thank you very much for having me here. So yeah, I'm a PhD student working on AI education. And today's my presentation is entitled Learning to Teach Humans and Neural Networks. So this title might seem a bit odd, right? Because teaching is a term that we use normally for humans, right? Not for machine learning algorithms such as neural networks. Neural networks, we use most commonly the term learning, right? We say that machine learning algorithms, neural networks actually learn, but we don't use the term teaching, right? So in this presentation, I'll try to show you that if we define the act of teaching as an optimization problem, it's quite restrictive, right? But if we decide to define teaching as an optimization problem, totally makes sense to talk about teaching for machines, and it can actually help understand and compare a lot of strategies that we have in each field. So this is not going to be a presentation with experiments and results. Maybe it's going to be a bit more abstract, but hopefully it might, also help you get some global perspective on a lot of stuff that we do in a few research fields related to AI and education. So I'd like to start with some small and simple definition of teaching. So that's one definition, right? Because of course it's very difficult to define teaching. It depends on a lot of stuff depending on what you want to put your attention on. But if we try to characterize formally in the simplest way possible what teaching is about, we can say that somehow teaching is the process of choosing a sequence of pedagogical actions to maximize the performance of the student while minimizing the cost. So a lot of terms that we do not define here that are a bit abstract, a bit vague. Pedagogical action, what do we mean by that? Performance, what do we mean? Cost, what do we mean? So it's a very simple definition, but I want to insist on this term cost because we don't often explicitly mention it. But there's always a cost to learning, right? It's never free to take pedagogical actions, and it's always about a balance between the performance of the student that we want to have at the end of the learning trajectory and the costs that we pay to achieve this performance. So, yeah, this definition is quite simple, right? And it might even look too restrictive, right? I mean, the mission of a teacher is so much more than this, of course. But the fact is that this very simple definition actually matches a big diversity of research fields. So the first one we can think about, of course, is adaptive teaching. So there are other ways to name it: intelligent tutoring systems, adaptive learning, etc. So basically, the idea of using educational technology to personalize human learning, especially in e-learning platforms. So this is very much related to humans, right? Human learning. But it's actually the only one I'm going to mention here, because all the other fields that I'm going to talk about are more related to machine learning. So one famous one is curriculum learning. So the act of ordering the training data for a machine learning algorithm from the simplest to the hardest one, to smooth the learning, to make it more efficient. A couple of other ones: self-paced learning, reinforcement learning, automatic curriculum learning, unsupervised environment design, active learning. So all these are research fields that somehow are related to this process of taking a sequence of pedagogical actions to maximize the performance of some agent that we will call the student. But as I'm sure you understand by now, is not necessarily a human. So yeah, we're not going to talk about all of these research fields here. I just want to say a few words about some of them, just to give you some understanding of what it's about. And then after that, we'll try to understand how they relate to each other and how we can compare them, and whether some mathematical framework can help us characterize, point out precisely where do they differ, if they're all, doing the same thing, doing teaching. What's the difference between them? So I'd like to start with active learning. So I think it's fair to say that active learning, so it's a research field in machine learning that I think it's fair to say that it started in 1987 with the seminal paper by Dana and Lewin, learning regular sets from queries and counterexamples. So what is it about? Very quickly, so active learning is basically the idea that a machine learning algorithm can learn better if it's allowed to choose data from which it learns. Okay, so I took this visual from a survey paper from by Settles. So the idea is that you have a data set of labeled data, and you use these data sets to train a machine learning model. Okay, and then you use this machine learning model to query new data to be labeled by an oracle, typically a human annotator. And then you use this newly labeled data from the oracle to complete your label training set, and then you train your machine learning again, and so on and so forth. So that's the idea. The core idea is that the model that you're training is able to choose the data on which it's going to be trained. Okay. And there's one word that I want to highlight here is the word better. A machine learning algorithm can learn better if it's allowed to choose data from which it learns. What does it mean to learn better in active learning? It means that we achieve same performance, but with less labeled data. So that's really the core focus of active learning: selecting data, selecting somehow teaching actions to make the training more cost efficient in terms of data. Another research field that we can mention here is curriculum learning. So somehow curriculum learning is more recent. I mean, it has been formalized more recently in 2009 by the seminal paper from Joshua Benjo. But it builds up on ideas that are much older. So what's curriculum learning about? It's similar to active learning. So curriculum learning states that a machine learning algorithm can learn better if we organize the training from simple to difficult examples. That's the idea, the core idea of curriculum learning. And again, here we have the term better. So what does it mean to learn better, to learn more efficiently in curriculum learning? It means learning with less computational cost. So somehow it's the same term, but it means something different. Computational cost, for instance, when you're training a neural network algorithm, you use techniques such as curriculum learning to reduce the amount of weighted steps that you're going to perform for optimizing your model. Okay. Another research field that we can talk about here is reinforcement learning. So reinforcement learning, in a way, it's much older than the previous ones, because I think it's fair to say that it started in the 30s with Bandit's algorithm, Thomson work, etc. So what's the idea of online, at least online reinforcement learning, because there's also offline reinforcement learning, but we're not going to talk about this here. Online reinforcement learning, the idea is that basically you're going to collect data by making your model interact with an environment, and then you're going to train your model on this data, and then you're going to use your newly trained model or some other behavioral policy related to it to collect again new data and then train your model on this newly collected data again, and so on and so forth. So an example that I like to use is that, okay, let's suppose that you want to train an autonomous car going from point A to point B. So what you're going to do is that first you're going to collect some trajectories completely randomly, and some of these trajectories are going to end up quite well. Some of them are not going to end up super well. And the idea is that once you've collected this data, you're going to train your model, reinforcing the trajectories that worked well. And then you're going to collect with this new policy, this new model, you're going to collect new trajectories. And again, you're going to reinforce it by putting more probabilities on the trajectories that went well, and so on and so forth. And at the end, hopefully you have a model that is achieving the desired behavior. So that's reinforcement learning. So again, a bit like curriculum learning and active learning, you find this idea of, collecting data, choosing data intelligently in a way that improve the training of your model, your student model. Okay, and one last research field that I want to mention, because I cannot not mention it. It's adaptive teaching, adaptive learning. So it's difficult to say when it started exactly, because there are many sub problems in adaptive teaching. But we can say that in the 70s came the first intelligent tutoring systems. So these systems to make learning more adaptable, more personalized for students in e-learning platforms. So what's the idea of these systems is that intelligent tutoring systems are systems to automatically optimize online learning sessions by taking sequences of pedagogical actions. And again, there are many sub-problems related to that. We can mention cognitive diagnosis, knowledge tracing, learning path personalization. I want to stress more on learning path personalization here because it relates much more to what we're going to talk about. So let's suppose you have an e-learning platform with a bunch of educational documents, pedagogical documents in it. The idea of adaptive teaching is that you're going to try to come up with a policy, with a strategy to recommend sequences of educational documents, of pedagogical actions to show to the students that connect to the platform in order to maximize, for instance, learning gains of the student. So, yeah. So for sure, all these problems, all these domains, all these research fields are pretty much different, right? But somehow we can't help but notice that they share some characteristics. For instance, all of them are sequential problems, right? You take actions sequentially in order to achieve some goal. And another thing that they share in common is that it's always about taking optimal actions, optimal in a certain way, to improve the training of some downstream model that we call the student. So, it's intriguing, right? These are separate research fields. They don't always, communicate with each other, but somehow we can see some high-level similarities between them. So the question that we can ask at this point is, can we come up with some common mathematical framework to unify these domains, to put them under a common vocabulary, understand what they have in common, and maybe try to point out where their main differences lie. So in our work, we propose to unify all these domains, all these problems, under a mathematical framework that we call a POM-DP. So what's a POMDP? So POMDP stands for partially observable Markov decision process. So what is that? A POMDP, so basically it's a mathematical framework to describe the behavior of an agent interacting with some environment. Okay? So you have an agent, it's going to interact with an environment, and you want some mathematical framework to describe, to characterize the modalities of this interaction. So a POMDP is fully characterized by a few components that I want to describe. So the first component is the observation space. Second one is action space, the objective, the state space, and a few others that I don't want to highlight in this presentation. I really want you to focus on these components, on these characteristics. So what does it say? It says that, so basically, a POMDP describes the way an agent can interact with an environment, and the way it does that is fully defined by these components. So if you answer to these questions precisely, you have a POMDP. So these questions basically say, so what is my agent able to observe? What is my agent able to do? What kind of action is it able to do in this environment? What's the objective of my agent interacting with this environment? What's the state space? So state space is basically the amount, I mean, the set of states that the environment is able to take, etc., etc. So I'm going to take an example so you understand more concretely what it's supposed to model. So let's take an example of one simple POMDP. Let's suppose that you want to train an agent to get out of a maze. Okay. Basically, you start with some initial state. Okay, at some point in the maze. But the agent, so the agent is going to take actions to try to get out of the maze, to find the exit, but it's not able to observe its true state, right? For instance, if it's a, I don't know, a first-person view game, it's just able to see what's in front of it. Okay, that's the difference between the observation of this and the state. The agent is in some state, but it doesn't know everything about it. It just has some, limited information about its immediate environment. So it has some observation. It's able to observe something, and then it's going to take actions based on this observation to try to change its state and try to achieve its final goal. Okay, and so this action combined with the previous state is going to fully determine the next state in which the agent is going to go. Okay, and so yeah, here for instance, it decided to go up, so it gets up and it ends up in a new state. Okay, from which it's able to observe so something different. This is the new observation of the agent. And then, okay, this is my observation. So I'm going to, this time I'm going to go right. And then I'm going to end up again in a new state and I'm going to observe something different and so on and so forth. So that's basically the idea of a POMDP. A POMDP is just a mathematical framework, okay, to describe the way an agent can interact with such environment by defining precisely what are the set of possible states, what are the possible observations, how the observations relate to the state, which actions I'm able to take, what's my goal, what's my objective, etc. So that's a POMDP, and that's a way of modeling interaction of agent with an environment. So how does that relate to our framework and our application here? So the idea is that we are going to model the act of teaching, okay, as a POMDP. A POMDP where the teacher is basically going to play the role of the agent. Okay, the teacher is going to act on some environment, and the environment here is going to be the student. Okay, and the teacher is going to interact with the student in order to achieve some goal. And now, so we have to define in this setting, what do we mean by observation? What do we mean by action, objective, etc. But it's very simple and very natural actually. Here, So our agent is gonna be the teacher. Okay, this is the agent that's going to take actions, and it's trying to make the student progress. Okay, it's going to be to make the student as performant as possible on some set of tasks. And so to do that, of course, it's not able to observe the brain of the student, right? To know exactly what the student knows and what the student doesn't know. So in this state setting, the observations are basically going to be some stuff like exams or tests, etc. So at the beginning of the interaction, the student is not very good, but the teacher, so based on this observation of the student, is going to be able to take some teaching actions that we will define more precisely later, but it's going to be able to take some teaching actions, and this teaching action combined with the previous state of the student is going to fully determine the next state of the student. And again, the teacher is not able to observe the student directly. It's going to observe some tests, some score at an evaluation. And again, based on this new observation, it's going to take some teaching action. It's going to determine the next state of the student, etc. And hopefully at the end, if the teacher is going to be able to improve the performance of the student. So I didn't talk much about the objective previously. So let's define this part more clearly and more formally. So remember the definition of teaching that we've used in the previous slide. So we said that teaching, so it's a sequence of pedagogical actions to maximize the performance of a student while minimizing the cost. So basically, the goal, the objective of a teacher interacting with this environment has an objective that is a balance between the performance and the cost. So what's the performance here of the student at the end? So, okay, that's quite obvious. It can be defined as, just the result of the student at the last test that he was able to take. But another important aspect is the cost, right? What did it cost us to achieve this result? So here, typically, maybe it took 10 years to achieve this result. So it's a huge cost, right? It has to be taken into account when comparing teaching strategies. So yeah, that's for adaptive teaching. And the nice thing about this is that sorry. So the nice thing about it is that it translates also super well, super naturally in the other research fields that I was mentioning previously: curriculum learning, active learning, reinforcement learning. Because in all of these research fields, it's kind of the same thing. Somehow we are the teacher. At least the training algorithm is going to be the teacher, and it wants to make some model better, more performant at some task. And so the modalities are going to change slightly. The components of the POM-DP are going to change slightly, but they are going to stay more or less the same. What I mean is that, so here, the model that we want to train, basically, it's going to be a neural network. It's not going to be a human student anymore, but the observation still, it's going to be about evaluating the neural network on some task. For instance, if we are working on a task of classification, we can measure the accuracy of the neural network on this task. And here, the teaching action basically will consist in selecting data, selecting examples on which we want to train our model, on which we want to train our neural network. And again, here, we can define the objective in terms of a balance between performance of the student, so of the neural network that we're training, and the cost. Here, the final performance is 0.77. And the cost, we can say, for instance, that if the cost is a computational cost, it took us 2 steps, to achieve this performance. So yeah, this slide is really about trying to show you that these problems that we describe, curriculum learning, active learning, adaptive teaching, etc., mathematically, they can be framed in a similar framework. So what's the point of doing that? So the point is that, So that now that we have framed all these domains within a common vocabulary, saying, okay, all these domains are basically from these defined in a certain way. We can use this common vocabulary, observation, action, objective, etc., to compare these domains component by component. And so I'm not going to talk about all the components, of course. I just want to mention one or two. So one very important component that's the source of diversity among all these problems is the observation. So basically, all these domains, curriculum learning, active learning, elective teaching, etc., want to optimize some teaching process, but one major difference is that they're not allowed to observe the same thing about the students. They don't have access to the same data about the learning, about the knowledge of the students. And that's the source of very different strategies. So curriculum learning, typically, so it has access to evaluation of the student on a full set of questions, on the full set of questions that we are interested in, the full set of examples. That's one of the axioms of curriculum learning. Active learning, on the other hand, only has access to evaluation on questions that it previously asked. So it means that during the training, active learning selects data on which to train the model, and it only has access on the performance of the student on this data, which is, much more restrictive than curriculum learning, which has access on the full set of questions. And we can also compare it to adaptive teaching. So, the act of training a student in an online platform, that's actually even more restrictive. In adaptive teaching, we have no evaluation available since in a way we pay for them. It means that when you train a student with an ITS, with an e-learning platform, every time you evaluate the student, every time you want to assess their knowledge on some skill, it's gonna take time for the student, okay? And somehow it's part of the cost, okay? It's part of the cost, and we have to take this into account when we designed automatic teaching strategies. Okay, so that's one aspect. Maybe one last one that we can compare is the objective. So as I said previously, the objective in a teaching task is always a balance between the performance of the final performance of the student that you're able to achieve and the cost that you pay to achieve this performance. And so in curriculum learning, the cost is basically a computational cost. We want to select data in a way that we reduce the computational time of the training. In active learning, the cost that we pay is typically the process of labeling new data, because we ask an oracle to label data, and that's what we pay for the training. And in adaptive teaching, the cost most of the time in the scientific literature, it's more like the session time. So, okay, I can take this pedagogical action instead of that one because it's more efficient, but be careful, maybe this pedagogical action is going to take much more time than the other one. So maybe the other one was less efficient, but maybe it was also, more, maybe it was just faster. So yeah, all these need to be taken into account. Not sure I'm going to talk about this. Okay, maybe just a few words. So another important source of differences between all these domains that I mentioned is basically the ability to sample students from a population in order to improve the teaching algorithm that we are using. I'm going to give you an example. Typically, in curriculum learning, active learning, reinforcement learning, etc., we want a teacher, so a selector of data, a selector of teaching action that is basically able to evolve with the students. Okay, both of them evolve simultaneously, because in these domains, usually we are only interested in training one model, in training one neural network, in training one language model. We don't want to design a teacher that's able to select data optimally for a wide variety of student models. In contrast, in adaptive teaching, typically, we train a model on a population of students. It means that basically we are able to try teaching strategies on multiple students and select the ones that work the best. So typically, at some point of its evolution, the teacher is confronted to one student. He's trying to take some pedagogical actions. Okay, maybe it doesn't work very well, but in the next student, for the next student, I'm going to be able to, adjust and make the strategies better. And hopefully, at the end, I'm going to be a super efficient teacher. So that's another big source of difference between adaptive teaching, where we always assume that we have a population of students on which we can train our teacher, and other domains like curriculum learning, active learning, etc., where usually we do not assume we can restart the training on new students and we have to be efficient right away, which is much more challenging computationally. Okay, and that's my last slide. So all this was to show you the diversity of teaching problems, and more precisely, what are the sources of this diversity mathematically. And we've seen that, so a big part of this diversity is related to what the tutor is able to observe about the students, but also what costs you the most during training. Is it computation? Is it the labels? Is it the session time, etc.? So all these characteristics have impacts on the strategies implemented in practice to optimize these teaching problems. And one of the reasons why it's more and more important defining precisely the teaching problems, especially in machine learning, not only in education, but also in machine learning, is that it looks that somehow there is more and more consensus in the academic community that we are running out of data. What I mean is that these big foundation models, language models, vision models, vision language models that we are training, they are trained on a huge data set coming from the internet, etc. And it looks like from the recent results that we are somehow running out of data, that it seems that this strategy that just consists of scaling the model, so increasing its size and increasing the size of the data set, it's showing its limits, right? And in this paradigm, so people who are working on this and who have been able to claim these statements, they compare human data to somehow the fossil fuel of AI, where by contrast, synthetic data, so data generated by the models themselves, they would play the role somehow of the renewable energy of AI. So what does it all mean? This means that it seems that even in machine learning, we will soon be confronted to the necessity of training algorithms to teach themselves, right? I mean, we are going to use synthetic data instead of using the data that are widely available on the web and big data sets, etc. We're going to have more and more. If we want to improve these models, if we want to achieve superhuman intelligence, etc., we're going to have to rely on synthetic data generated by the models being trained. But when we do this, we enter a new paradigm, right? We are not the teachers anymore. The models themselves have to be the teacher for themselves. So yeah, algorithms learning to teach themselves. So yeah, these are quite important problems that I think will be more and more important as we realize that we are running out, on data on the internet, and this problem is very much investigated by some research communities. So the people that I'm mentioning here, David Silver, Richard Sutton, but also, more and more communities related to what we call open-endedness. So open-endedness is this idea that idea of training algorithms in a way that is open-ended. It means that it's creating more and more complexity for itself as it's progressing, and it's not relying anymore on some supervisor, such as a human, that decides what is going to learn at which time, etc. So yeah, all this to say that in the end, this problem of teaching is not just a problem for human learners. It's going to be more and more an optimization problem that's super important in the machine learning community. And that's it for my presentation. Thank you very much.
In the room. Online.
So, good evening. For the presentation. I'm wondering about the pertinence of measuring the quality of learning of students with simple indicators such as the ones you're bringing. It's very working very well for algorithms, where the end goal is very well known and measurable, but in real learning for humans, it's usually not the case. You have lots of externalities, and you do not want to learn like just facts, or that's the old way of learning, but now you want to learn actual skills that you can put in practice. And also you have lots of potential externalities, like if you train people to be good at getting A+ grades, but you make them like oblivious to everything else, it's actually really bad way on the objective way of learning.
Yeah.
So, how do you see it?
Of course, completely makes sense. I think that's one of the main limits, of this scientific paradigm, because during all my presentation, I pretended that teaching and education and human learning is just an engineering problem, right? And we know that, of course, it's not the case, right? We know that there is so much more in education than just trying to maximize some performance at some test. But if you want to frame this problem, if you want to train a machine learning algorithm to be a teacher that is as good as possible, you need to have some metric to measure that, some non-ambiguous metric. So at some point you have to say, okay, if I want to optimize my teacher on something, what should it be? What can be the best approximation, numerically speaking, of what the teacher has to do, of what is a good teacher, right? So we have to use some measure at some point. And of course, exams, tests, there are biased measures, they are very limited, very restrictive, but most of the time that's the best we have. But of course, you can use other measures, and in e-learning platforms, there are plenty other alternatives, right? For instance, people measure retention, people try to measure motivation, people try to measure, the activity of the students on the platform. And again, all these measures, they are very restrictive and they are not capturing the full mental state of the student. But that's the best we can do.
I'm an engineer myself, so I understand what you're saying, but I think it's quite dangerous to frame the problem of learning in narrow indicators like that. But actually, I agree with the end of your presentation when you are more like open the field on the ML side, where you say that algorithms have to become active themselves and to learn maybe between peers on by defining their own strategies. And look, actually, humans work best like that. And we're coming out of the age where you had to cram facts into their head, like beginning of ML, and going to the age where you go out and learn to do by doing some activities and choose your own objectives and learn with peers. And
well, in the end, all these, machine learning algorithms, whether they are open-ended or not, are inspired by biology, right? So I mentioned the domain of open-endedness. It's full of biological principles, like genetic, like social interaction, etc. People working on that are really trying to inspire from what they observe in biology to try to, synthesize these processes in training, in the training of machine learning model. But yeah, I'm not sure it answers the question. What was it again?
Small comment on the question.
Yeah. But yeah, so now regarding the fact that it's dangerous model tuning that way, I think the danger is to use these algorithms while not being able to see their limitations, right? I mean, we should always use these algorithms knowing what they can do and what they cannot do, and just trying to responsibly use them that way. But yeah, at some point, so as I'm sure you're very familiar with, if you want to design an optimization procedure, you have no other choice than relying on some score, some evaluation.
Questions, Monica?
Thanks, Jean, for your presentation. I have a question about your definition of teaching. I'm trying to understand exactly what you like. Okay, you come from the computer sciences, I come from the human learning sciences, and I'm trying to understand a little bit more where this definition comes from and what allows you to say that minimizing the cost is better. Because this notion of cost is also present in the human learning sciences, but there's a theory in psychology called cognitive load theory that has been here and there for a while, and there's a lot of evidence that cost is actually fundamental in human learning. But psychologists differentiate different types of cognitive load, so different types of costs. And it doesn't mean that because cost is important, minimal cost is always better for learning. And there's actually a lot of evidence that learners need some difficulty, some load, but it's a special type of cognitive load that they name germane load, which is different from extraneous load, which is a cost that is related to things that are not helpful for learning, such as, for example, when you present information in unordered manner or unstructured or with lots of visual details that are not relevant for learning. This is the extraneous load that is not relevant for learning. But germane load is when you just challenge your learner enough so that it will help them establish connections in memory between what is just learning and knowledge already stored in long-term memory that will generate also long-term memorization of the new content. So this notion of cost in learning in the learning sciences is also central, but there is no evidence that minimizing the cost is always better for learning. So I was trying to understand the definition, where it comes from, and whether you apply it for machine learning or also to learning.
Yes. So thank you. No, thank you very much for the comment. It's super interesting what you're saying. So of course, this definition is trying to be as general as possible. So of course, it's making simplifications, and maybe the terms sometimes are not adapted to this or that domain. So when I use the term cost here, it's really like a general notion to try to encapsulate something that we don't want to have. And so if I understand correctly what you're saying, here you're saying that in the domain that you're referring to, the notion of cost is not necessarily something negative, and we don't necessarily want to make it as minimal as possible. I think that in this case, if we want to relate that to this definition, the cost that we're talking about is not necessarily something that we would put in the cost, but maybe something that we would put it's something that we want to maximize, but maximize in a smart way, right? I think the difficulty here is to make the difference between the objective that we want to achieve and the surrogate objective that we implement to achieve this final objective, right? So in education, most of the time, we don't optimize the final objective directly. Let's suppose that the final objective is to maximize retention with, I don't know, minimal training time, for instance. Let's suppose that. But this is an objective. That's the real objective that we want to achieve. But this is a very sparse objective. And even when we optimize algorithms for this objective, usually we don't use this objective explicitly. We use a surrogate objective, such as, for instance, recommending taking teaching actions that have intermediate difficulty. I mean, what we're describing, for instance, it makes me very much think of the zone of proximal development developed by Vygotsky, which consists of trying to take educational actions that are not difficult or not too easy. Okay, I think somehow it relates to this balance that we want to find with the cognitive load that you mentioned, but maybe we can discuss that later. But this is different from the final objective that we want to optimize. When we take actions in the zone of proximal development, when we try to take actions of intermediate difficulty, it's not because we want to take actions of intermediate difficulty. It's because we want to make the student progress as much as possible while spending minimal time in the learning platform, right? So in this setting, we are optimizing an objective that is a proxy for the other objective that we want. The proxy is trying to find the best intermediate actions to take for the student, the best intermediate difficulty for the student. But the long-term objective, the reason we are taking this intermediate action is that in the end, we want the student to be as performant as possible while avoid taking actions that are not good for his learning, like taking too much time or etc. I don't know if this answers very well, but the problem with this definition is that it's trying to give some framework to separate in the final objective what we want to maximize and what we want to minimize. And I use the term performance and cost, but maybe sometimes they do not exactly relate to the terms that we use in downstream domains. Does it make sense?
Yeah, I think it is. Much of it is about what you call cost.
Mm-hmm.
What do you put behind the word cost?
Yeah, exactly.
Because you spoke about time, for example, and there's also a bunch of research showing that
Of course.
repetition, study sessions with longer periods are actually better for memorization, for retention, and for learning overall. So
That's why we have to be very careful with these terms. When we put something in the cost case, it has to be something that's really undesirable. And sometimes we have to make approximations, right? Sometimes when we want to train a machine learning model, we have to put in the spot, we have to consider as cost something that's not necessarily such a big cost, but for the sake of simplicity and make the training easier and make the optimization problem easier, we put it there. So it's the end. In the end, we have to make approximations. We have no choice, right? It's the same as the previous question. Like when we measure the evaluation of the student, okay, then we say that the best teacher, the best automatic teacher is the teacher that will make the student have the best score at the final test. But that's not really what a good student is, right? It's just a proxy, right? So I think what is really difficult about this domain is that we are trying to quantify and to measure objectively something that's more subtle and more, diverse than that. But we have to say something. We have to approximate something because otherwise we don't train any model, right?
questions?
Thanks a lot. It was very illuminating to see that work, and I didn't know that intersection in those two sides of education. And it made me wonder as a teacher also, when we teach, we always teach a population, and there's different levels, different progression. And so we need to make decisions indeed on, decisions on what level we're going to teach, whether we're going to do one-on-ones with certain people, etc. And so there's kind of a collective population wide process. And at some point you talked about the population side of things, but I was wondering whether there was any insight from the more like computer science thing on how you build these cost function, or like these decision steps on how you co-evolve with the population, like 80 or like 20 to 80 students, not just one, right?
Yeah. So yeah, I guess this relates more to the episodic paradigm that you mentioned at the end. Yeah. So okay, that's a very important distinction because the POMDP that I mentioned, so this mathematical framework, is not enough to fully characterize the difference between the machine learning problems that I described, curriculum learning, active learning, reinforcement learning, etc., and the adaptive teaching problem that most research papers of AI and education tackle. And the main difference is this, is that in education, we usually assume that our model is not confronted to only one student, it's confronted to a population, and it can use this population to improve its teaching strategy. And that's actually a huge problem, because it basically means that not all the students are going to be treated equally, right? So there are multiple ways, to balance that. For instance, we can say, okay, we have a target population, and there is one other population of students, of people who are just going to be used to train the policy, to train the teaching policy, to make it as efficient as possible. But so somehow it's related to the problem of sample efficiency. So how much students are required to train a good teaching policy, and that's a very important measure. So, for instance, a couple of months ago, I've read a paper by Amazon where they train a reinforcement learning policy to take pedagogical actions optimally somehow, which means that the students, score as good as possible at the end of the teaching session. And I think it took them something like 1,000 students to achieve this result. So they needed a population of 1,000 students just to train a small neural network, to sequence pedagogical actions optimally. So the whole point of my presentation is to say that when we compare educational policy, educational strategies, this has to be taken into account, and this is super important criteria for comparison between teaching policies. And it's at the core of the evaluation. But I think these methods and insights are make much more sense for automatic teachers. I don't think that these methods and strategies and evaluations are very consistent, and I'm not sure they make sense in real life settings when one teacher is confronted to one class. That's also.
Just maybe because for the sake of it, your cost is mostly about the teacher cost and not the student cost. Why?
That's a really good question. So we are trying to evaluate the teacher here. We're not trying to evaluate the student, and that's very important. We are comparing teaching strategies, right? And we have formalized precisely mathematically what we want to maximize in a teaching strategy and what we want to minimize, right? And most of the time, you have to find a balance between both. Basically, I just said that you have to strike a balance between performance and cost, but there are measures actually that formalize that. I mean, there are a couple of measures that are very much used in the literature that propose some standard way of balancing both. But yeah, coming back to your question about the cost, I'm not sure what was the question.
Yeah, if for example you just take into account the teacher cost,
Yeah.
if the teacher is 1% more efficient, but at the cost of the learner spending 15 times more, with your optimization, it will be seen as better, but it is not. If
If teacher is 1% cost,
only if you improve the teacher, if a method for the teacher is 1% better from his point of view, like
it's better for one.
it has
better for
the
1%.
50 more time spent by the learner, for example. In real life, it would not be seen as a gain, but in your algorithm here, yes.
Sorry, if I understand correctly, you say that sometimes the teaching strategy can be better for 1%, but
It's really like there are two types of costs. There's the time spent by the teacher and there's the time spent.
there are many types. There are many types of costs. I mean, this framework is an abstract framework, okay?
Yeah.
And you can define as the cost whatever you think is important and undesirable in your teaching framework. That's the whole thing. And basically, actually, people do that. I mean, in research, when you look at adaptive teaching papers, I mean, papers on intelligent tutoring systems and AI for education, etc. This notion of cost is always used implicitly, like when they compare teaching strategies, algorithms for recommendation, etc. They're always comparing them against something. Okay, this algorithm is better than this one, but what did it take to get this performance? I mean, okay, the simulated population of students confronting to this teacher is better with this teacher than with the other teacher, but at which cost, right? Maybe, I mean, if I don't define a cost, it's very easy. I can just say, okay, I'm just going to take some random teaching actions forever, and in the 1 million years, I'm going to have Albert Einstein as a student. So, okay, that's great, but look at the costs for having Einstein. Maybe it's better to have someone that is less intelligent in just a few days, right? So that's in all papers that compare teaching strategies, this notion of cost is always at least implicitly defined. Does it make sense?
Doesn't have to leave, but he wanted to leave a comment. Fantastic talk. In relation to the idea that it is dangerous to define it in this way, I agree at one level, but from another aspect. I wonder if the required rigor of creating a computational definition of learning as optimization can also inform skepticism and humility about the possibilities and constraints of and limits of rigorous scientific methods in curriculum design. That is, the danger is not in computation, but in measuring what matters and knowing those limits in general. From my view, your work is critical to allow clarification of what is optimized or computable more generally, outside of machine learning comments. Just wanted to share that with you.
I cannot agree more.
So he was really pleased with the talk, and I'm thinking we'll reach out.
We know this.
Yeah.
I can connect you.
Yeah, but you have to be already, but we can connect you. It's just really like the guidance.
All right, I think this is a full hour. Thank you very much, y'all.
Thank you so much.